So this is the essential idea, and then using that, of course, one proves that, for example, if mod z is greater than norm A, then say z minus A inverse, this is in A, and so on, so forth. Other crucial idea was, yes, always, unless otherwise specified algebraic identity. And then, of course, other essential idea was the application of course, after this we introduce the concept of spectrum, and then application of Liouville's theorem to show that this is non-empty. To prove that it is compact and closed and so on is essentially these ideas. And after that we have this concept that if F is holomorphic, in a neighborhood of spectrum of X, then where this integral is defined as limits of Riemann sums, this quantity extends the usual this idea of functions of elements of this is called function calculus. So if we have a polynomial map, then we can form Px equal to x power k. But this idea is extended to this, and this map f going to fx is a homomorphism. From this is holomorphic functions in a neighborhood of sigma x to the algebra A. Now, of course, for polynomial maps, we proved a proposition that if P is a polynomial, then spectrum of like spectrum of PA, so that is also extended here. And this is called spectral mapping theorem. So proof is also same as the other one. So suppose lambda is not an element here. So we have spectrum of X, then of course this is so this is open and it maps this holomorphic map. So if we will map this open set to open neighborhood here, and outside. So kind of we can form this function that g, which is z going to 1 by lambda minus fz. So this function is defined in a neighborhood of sigma x. So is this is analytic of this, and now if we call this function h of z equal to lambda minus fz, then h dot g at z equal to 1. Now of course we know that this is a homomorphism, and this is nothing but hz times zz. So that property says that hx times gx equal to 1. What is hx? Hx is lambda minus fx 1 by, or that is incorrect, that is the idea. So this times gx equal to 1, therefore belong to fx. So this proves this implication. Now to prove the other way, suppose if lambda is in f of sigma x, that is lambda equal to fz for some z in sigma x, we do as we did last time. So we expand this quantity. That is the function calculus, right? F going to fx is a homomorphism, therefore, okay? This is the point that you can talk of functions of operators or algebra elements, and whatever relation is there in the function level should persist. No, meaning this is quite. So you expand this quantity, and this is u minus x inverse minus okay, let us be careful here. So kind of there is some confusion being created, and that is intentional. This x is an algebra element and this z is a complex number. Okay, they may look like all same, but this is an algebra element and this is a complex number. So, but this is intentional. So, at the next stage we want to do a simplification, and the rough idea of the simplification I explain, and then of course we will verify that. So let us treat at this moment x as a complex number, and that is the spirit of this manipulations anyway. So you write down it like 1 minus u minus x minus 1 by u minus z, and then of course it is like, I did this yesterday also but did not spend much time in explaining. So you write it, and then of course it is u minus z minus u minus x. These two things cancel, and therefore this is x minus z by u minus x times u minus z. So let us write it in our algebra language now, because we do not know what is 1 by u minus x, that stands for u minus x inverse, minus everything is a function of x, therefore all of them will commute. Is everything all right? Meaning this is u minus z minus u minus x, so x minus z, u minus x, u minus z. So this is u minus z inverse, x minus z, u minus x inverse. Okay, so now we want to prove this identity we want to prove in the Banach algebra. Of course, that means that we multiply this from this side. This will happen even only if we multiply this one from this side by u minus x and okay, so 1 minus and u minus z. So you multiply it by u minus x times u minus z, this will give you this will give you that, and this will give you x minus z. So this is true and therefore this is true. So we substitute u minus x in u minus z. Okay, there is a problem of a, no, this is okay. So this is equal to, so I want to pull out this z minus x. This does not depend upon this u, so it comes out. So call this entire quantity something. Now of course, but this is a function of x, therefore this one, these two elements commute, that is the only point. So these two things commute and therefore this is invertible will imply z minus x is invertible, and that is a contradiction. So, or other words, as z belongs to spectrum of x implies lambda belongs to spectrum of fx. So this shows that f of spectrum of x is contained in spectrum of fx. And one can compose such functions. So if so this says you form G, fx is an algebra element, so you can form G of that, or you can form this function G compose f and you can evaluate this at x. These two are same. So you have, this is like spectrum of x. This is an open set on which f is defined. So this is domain of f, and this is spectrum of fx, and here maybe G is defined. And of course, as f is holomorphic, f of this is another open set containing this. So you would draw a curve this set is f of domain of f. So you draw a curve, this is C1, inverse image of C1, of course it is within this intersection, smaller thing, so you can bring it back here using f, and it is a compact set. So you draw another curve C2 which encloses this. So this is f inverse of C1, and this curve is C2. So C2 encloses f inverse of C1. Then you start computing using and instead of writing lambda minus x inverse, I will write lambda minus x like that. Huh? Which one?
What is f inverse C1? Why is that a curve?
That it could be anything. It is just set.
It will intersect sigma x also.
It could intersect anything. It could be like this, whatever it is. But it is a compact set. It is a compact set, and it is a compact set, and R which encloses that. That's all.
That's C.
Which C?
Here is no C.
Which one is C?
No, in the integration you have written C.
C1. C1 will do that. C1. Yeah.
Just wondering that what is this line 2 from below?
This is the
Why Hx was invertible?
who said Hx is invertible?
That
Z minus
one element is invertible if not.
All you need to know is that these objects, this is a function of x. So limits of polynomials in xn. Therefore, this object.
Yes, we can't use H. We'll do something.
In this proof, there is no other h. In this proof, there is no other h. Or if you do not like, then you put this symbol. It is h of this. It is some other function. So it is a x. That's all. So this is g of f lambda, you expand, and then it is g mu by mu minus f lambda d mu. I said yesterday in this game you interchange limits freely because yeah. So this finishes this, and now of course we will concentrate on abelian Banach algebra. We will drop this condition of unitality. So A is abelian and not necessarily unital. So we have an ideal M, and it is called regular if there exists an element E in the algebra such that Ex minus x belongs to M for all x in A, or equivalently this algebra is unital. If we have something like that, then yeah, so elements from M cannot go too close to E. Okay, so if M is a proper regular ideal and E an identity modulo M, then so suppose the contrary, that is so then you consider this quantity so because of this condition this sum converges and this is an element of the algebra A, and then of course you observe that so you have this equation how simplify this is EY minus XY plus E minus X. So you fix an identity here, pull it up in A and call that element E. That's all. Ex minus x is in M. That means that, right, it is the same equation. Yeah. So E equal to y minus EY plus x plus xy. Now, by our condition, this element is in M, this is in M, this is in M, therefore, this is in M, and now I can write A as A minus EA plus EA. Now, this is in M, E is in M, therefore, this is in M, so this implies. So, this contradicts this fact that M is proper. So, consequence of this proposition is the following, that if we start with a proper regular ideal, then its closure is also a proper ideal. That is the consequence. Okay. So, the closure of a regular proper ideal is a proper regular ideal. So, it is proper because of that condition, and it is regular because any ideal containing a regular ideal. So, any ideal containing a regular ideal is regular. And another consequence is the following, consequence of this consequence actually, that all maximal ideals, meaning proper maximal ideals, proper maximal regular ideals are closed. Okay. And then any proper regular ideal is contained in a maximal regular ideal. Proof of this is you fix an identity modulo M, and then of course that remark, any ideal containing M is regular. So now to ideals not containing E. Then of course all these propositions are like kind of parallel to whatever we did. Not containing E. Of course, E cannot be in the ideal, right? E is a unit of the quotient space. Which one? Suppose you are given proper ideal, okay? So, M is a proper regular ideal. That means what? That there is some element E such that X minus X belongs to M for all X in M. So, if I take any other ideal N, that is regular. Okay? So, I consider all, so any other ideal containing N is regular. I consider all ideals which contain M and does not contain E. Okay? For this proposition, we do not need commutativity. So, let M be a closed ideal in a possibly non-commutative Banach algebra A, then of course as M is closed, so M mod M is a Banach space and it is an algebra also. So this is a Banach algebra. So by ideal I mean two-sided ideal here. Proof. So suppose we have this quotient map and then this is the norm of the quotient space. So that means then of course you no. So this is pi of this times pi of that. So that is less than equal to norm of this product, because pi is contractive, norm of this product, that is less than equal to norm of x plus m times norm of y plus n, and instead of those two you put these two, and of course arbitrary. So so this proves this is a Banach algebra.
Phi of xy is some xy plus something. Phi norm of phi.
Which line?
You want to prove that this is a norm.
No, you do not want to prove this is a norm. That's it. That is functional analysis which you should have done. We are not proving this is a norm. We know AM is a Banach space. I am not proving that. This is a Banach space. Modulo a closed subspace is a Banach space with respect to this prescription for the norm. So only thing we are trying to prove is that if I take product of two elements here, their norm is less than equal to product of the norms. Okay. So we start with x and y. I write down norm of pi x pi y, that is same as pi of xy. So pi of x plus m times. So maybe I write down the. So pi is contractive. This is infimum, so I can put m equal to 0. So pi is contractive. So this is. This is the norm in my original Banach algebra. So I can put here, still that is okay. And Then I, instead of this, I put this bound, instead of that, I put that bound, as epsilon is arbitrary.
Different
Yeah, it is m, it is n. All are a kind of small remark, there is nothing more than that. Let A be a unital Banach algebra and so if A is a unital Banach algebra, A is not invertible, then X is contained in a maximal ideal. So, of course, you consider this ideal Ax, this is a proper ideal. So, so there will be a maximal ideal containing this. Suppose you have a non-zero homomorphism, then phi inverse 0 is a regular maximal ideal and is a bijective correspondence between non-zero complex homomorphisms and regular maximal ideals. So, firstly this A mod kernel of phi. So as phi is non-zero and it is a complex homomorphism, therefore this is isomorphic with C, which is like image of phi, and this object is, this is a field and it is of course unital, so that says kernel phi is a regular maximal ideal. And so you need to prove that this correspondence is bijective. So you use this fact that if something is a maximal ideal, then in the quotient everything is invertible. So let M be a regular maximal ideal. This fact that it is a regular maximal ideal, this implies that on A mod M, this is a Banach algebra. Firstly, every non-zero element is invertible, and of course this is the Banach algebra, so therefore we proved that if that happens then it must be C. So therefore if I define phi to be the quotient map, then phi is a homomorphism and yeah, is equal to kernel of phi. So suppose we have a non-zero homomorphism, then phi is continuous. So you look at this object, so it is crucial that C is a field. So then M is a regular maximal ideal, so M is closed and this map phi is actually the quotient map. And therefore phi is continuous. But meaning there is a norm bound for this, so non-zero homomorphism then mod omega x is so this is like omega x, this is a homomorphism, so omega x to the power n and mod to the power 1 by n. So that is and times norm x. So therefore, as n is arbitrary, maybe now I should stop and explain. It is kind of what are we heading at? So it is a general principle that if we have a so general principle is that we have a, now forget about Banach and all those. So A is a commutative algebra. Then we want to think of A as some suitable class of functions on some space, and of course more, or the space of maximal ideals of A. And first instance comes from commutative algebra and so on, so I do not want to enter into that. In this case also the idea is like producing a map from A to continuous functions on omega A or some function space. Let us put this within this. So this is the space of, we have already identified that maximal proper regular ideals, and that is same as non-zero complex homomorphisms. So you want to produce a map like this, and then want to understand this. This is a concrete object, so want to understand the image here or the space through this embedding. In general, it need not be an embedding, but through this map. So I have already introduced the notation. Let omega A be the space of non-zero complex homomorphisms. This is a locally compact Hausdorff space. So note that omega A is a subset of A star. So on A star you have the weak star topology. So you restrict your weak star topology here. With respect to that, it is a locally compact and Hausdorff space. So you throw this extra element 0 and then you prove that this is closed. So you consider all homomorphisms. You forget this restriction, non-zero. Okay, now we want to prove that omega prime is closed. So suppose we have a net omega I converging to omega, then this is the definition of weak star convergence, and so this is limit and that is same as. So this shows that omega is a homomorphism. Omega could be 0, could be non-zero. So prime closed, and this is this point 0 is a closed subset of so omega A is it is a open set in a compact space. So this is locally compact, and this is Hausdorff because then there exists some x such that omega 1 x minus this difference is greater than epsilon. Now consider these sets omega such that so these two sets are disjoint because it is within epsilon by 3 of this, it is within epsilon by 3 of that, but these two are more than epsilon apart. So these two are disjoint neighborhoods of omega 1 and omega 2. So this is a Hausdorff. A unital implies omega A is compact, so that is because zero is an isolated point, because for any other omega of 1 is 1. So now define this map, but yesterday anybody tried those two exercises? One is on the Fourier transform and the other was, of course, the other one is not related, but anybody tried the other exercise, norm may be less than or equal to m times norm BA? Yes, Kamalaksha, did you try? Anyway, so point of the other exercise on Fourier transform was really this definition. So for x is in A, This is a definition come proposition. So, we define this map x hat from omega a to c given by x hat of omega is this. So, this part is definition, and proposition is the following. If I denote this assertion by F, then image of this is actually C0 of omega A, and so assertion is x hat is in C0 of omega A, that is the assertion, and this is called the Gelfand transform. So, proof, firstly, continuous function, that is clear because that is from the definition of weak star topology, it is a continuous function. We only need to show that this 0 part, that it vanishes at infinity. So, vanishes at infinity means it is small outside compact set. So, if you so this is a closed subset. So, this is a so this is a closed subset of a compact set. So, therefore, this is compact, and this proves that, and this notation f of course comes from Fourier transform. So, if we take A to be L1 of R, then that exercise what that does is the following. It says that so exercise was, if I have a homomorphism, say phi from A to C, a homomorphism, then there exists, of course one can prove that, unique point T in R such that phi of f equal to integral fx e to the power I tx dx. So, we can identify omega A with R, and then this map f of f is so it is the Fourier transform, and this fact that this has a name called Riemann-Leibniz lemma. So, this general observation extends that. So, that is the spirit. It extends some of the harmonic analysis on real line or maybe abelian groups. For a unital, spectrum of x can be identified with the range of this function. And for a non-unital, one has to throw this. This point is extra, and one has to throw it. So, case 1, a unital. So, lambda belongs to spectrum of x if and only if x minus lambda is not invertible. As it is not invertible, that means it is inside some maximal ideal. That means it is inside the kernel of some homomorphism. So, it is inside some kernel of some homomorphism. So, that means that there exists some omega such that 0 for some omega, and that says x hat of omega equal to lambda. So, that is like this. A non-unital, in this case, of course, we discussed that this is a unital Banach algebra and so on. So, this will be the unitization of A, and omega of A tilde are homomorphisms. So, it contains, of course, all homomorphisms on A plus one more point. Because 0 homomorphism, if you set some homomorphism which is 0 here and 1 goes to 1, that is also a homomorphism, that is an element here that corresponds to the 0 homomorphism on A. Or you can take all the non-zero homomorphisms, say they will also induce homomorphisms here. So, now, and spectrum of x is spectrum of x as in A tilde. So, two possibilities, either omega tilde is from this part or from that part. So, if omega tilde is from this part, then of course lambda belongs to x hat of omega A. If omega tilde is from this part, namely 0, then of course lambda is in here. Yes? No? No problem? No, there is some problem. What is the problem? Tell me.
So, we said that if x minus lambda is not invertible.
X minus lambda is not invertible. That means it is contained in some maximal ideal. Maximal ideals are kernels of homomorphisms. So, there is a homomorphism on which this is 0. Okay. So, final part is this one. Of course, it is a. So, x hat is a continuous function, we can consider its norm, but that it just follows from this, right? Norm x hat is supremum mod x hat omega, omega is in omega a, but that is same as supremum mod lambda, and that is the spectral radius. So, if we combine all these parts, then what we obtain is that we have this map point number 2, spectrum of x is image if a unital, otherwise it is if a non-unital, and then so in general we know the following thing, that Rx is less than equal to norm x. So this map is contractive, and therefore natural question is when is this an isometry? So that leads us to the next topic, namely C-star algebras. So that is a convenient class, commutative C-star algebras, on which this is so. So in general we have this embedding, not embedding a map, and in case this were an isometry, then of course it will be an embedding, so it becomes somewhat concrete. So that is the spirit. An involutive Banach algebra A is a, of course it is a Banach algebra along with a conjugate linear anti-homomorphism whose square is identity. That means we have a map A going to A star such that lambda A star is lambda bar A star. It is conjugate linear. Anti-homomorphism means this direction changes. A B star is B star A star. Square is identity means A star star is A. So a C-star algebra is an involutive Banach algebra A such that norm x star x equal to norm x square for all x in A, and this identity is often referred as
So
system.
far you put no condition of continuity or any such.
No.
In,
Because I will be studying. Exactly, I won't be studying involutive Banach algebras anyway. So for sister algebras, it becomes
there you
isometric.
are not putting any condition.
No. Yeah, but as you have raised meaning, one often puts this condition that this is isometric. I always.
So you are putting.
No, I do not put that because we will
One
go.
can consider.
One can consider, yeah. Meaning Takesaki puts. We will be doing sister algebra, so. And, yeah. If this happens, then of course that is a consequence of this property. So let us verify that. So norm x star x is like norm x square less than equal to norm x star times norm x. So this implies norm x is less than equal to norm x star. Of course, it is true for. So you can also write norm x star, it is star star is x. Therefore, norm x star is norm x. Okay, so let us use this condition and so x is called normal if x star equal to x star x, and it is called self-adjoint if x star equal to x. It is called unitary if equal to identity. Okay. So I want to prove this following proposition, that if x is normal, then norm x is the spectral radius. So if some element is self-adjoint, so suppose y is self-adjoint, then that condition y star y equal to norm y square means that norm y square is norm y square and x star x is self-adjoint, so this happens. So we have and so this implies because every term is same as norm x. And of course, on exercise, let A be a Banach algebra such that norm x square is norm x square for all x. Then A is commutative. All these exercises are from routine actually, so you can do whatever you like. Okay, I just prove one more proposition and then I will stop. You note that I have not given any example of sister algebras, so one or two examples. Tomorrow we will spend a lot of time discussing examples. We won't do anything, any theorems or things like that, but we will discuss examples of various kinds. So first example is X is a compact Hausdorff space. Then you consider Cx, these are continuous functions. And you define f star of x is fx bar, then this becomes a sister algebra. Another example is H is a Hilbert space, then bounded linear maps. Now given element T, I want to define operator T star, so I have to say what T star does to a vector xi. So instead of specifying that, I specify what it does like that. So this prescription for all xi eta defines a linear map T star, and so BH with this involution is a sister algebra, and so you can consider star closed, norm closed subalgebras of BH, they are also sister algebras. And finally, we will prove that Every sister algebra is of this kind. So, yeah. Maybe I stop here today, and tomorrow I will discuss some more principles of construction and so on. What, any final doubts from Kamalaksha? No?
This algebra is either BH or CX.
No, I did not say that. I chose norm-closed subalgebras of BH.
Last one.
Is of this kind.